Okay, this is the 7th live session for AP Calculus Prep. And we've covered limits, and then we used the limits to define derivatives. And now that we've gone through the rules of derivatives, so differentiation rules, there are now things that we apply a derivative to. So we don't just have derivatives for the sake of taking derivatives, although that is kind of fun in itself. But there are lots of real world applications because the real world changes. And so if the derivative is basically essentially a tool that directly models, it can describe change and change in systems, then we can solve many, many, many kinds of problems. And so this week we have done implicit differentiation, which is an application of the chain rule. We've also done the first derivative test, which is really just a way to find the extrema of a function, which is a really, really powerful tool, which is then we actually kind of apply the first derivative test into optimization, because when you then solve an optimization problem, the whole point of optimizing something is finding an extrema, whether that's minimizing the cost of material for something or maximizing the amount of profit you can get given a certain model. Do you guys have any? This week's it's all a bunch of applications. So were there any things that you wanted to just see explained clearer, or anything that was particularly confusing before we get started? Okay, well, in that case, we can just start in order. And I'll try to keep the chat bar open on the side here. Okay. Let's start with implicit differentiation. Implicit differentiation. Something that happens many, many times is that we'll have some sort of equation. We'll have some sort of a system where in the equation we're relating functions of functions, basically. So we'll have several different functions in one equation, and all of these functions can be changing, right? And understanding how to relate those changes, implicit differentiation and related rates are very similar in terms of their concept. So implicit differentiation definitely leads into related rates, because when we do related rates, we're essentially doing one specific type of implicit differentiation where we implicitly derive with respect to some parameter t, so for time, in a related rate problem. Whereas with implicit differentiation, we normally just use x, and that's the independent variable. So did the procedure for implicit differentiation make sense when you were solving the problems, if you have started? And it's okay. So let's do a problem in class, just to make sure that we're all on the same page here. And then if actually what I might do is I might walk through a problem and then I'll have you do one. So if we have, say, sine of x plus cosine of y is equal to x squared y squared. And we want to find dy dx. We want to find the derivative of y with respect to x. And so what this tells us is, well, first of all, y is a function of x. Such that we have y of x. You can imagine it being like y of x equals blah, blah, blah. And we want the derivative. We want to find the rate of change of y with respect to x. And so the way we do this is we take all of our derivative rules that we've practiced and we apply them. And we simply ask ourselves, if we are doing something with a y in it, then we need to remember to multiply by dy dx because of the chain rule. So the derivative of sine x plus the derivative of cosine y equals the derivative of x squared y squared. Now, the derivative of sine x with respect to x is what? Right, we have cosine. Now, what's the derivative rule that we have for cosine? The derivative of cosine. What does cosine go to? What function does it go to when we differentiate? Right, it goes to minus sine. Now, like, I think it was Christina that pointed it out. It's that we are using the variable y here. So we have negative sine y. And then what do we do here? Because we have a chain rule. So we have a function and a function composed inside of another function. Y is a function of x. It's composed inside exactly. We then multiply this by the derivative of the inside function, and the inside function is dy dx. It's the very thing that we're looking for. And so that's the nice thing with implicit differentiation, is that it's actually a very simple application of the chain rule. And then over here, what kind of a rule are we going to first have to observe this as? Do you recognize? So if we have something, we have a function and we're multiplying it by a function. So to take the derivative, yes, exactly. We're going to need the product rule. And so the product rule is the left, the right, goes right, the left. So left, the left in this case is going to be the x squared. So we have left, the right, plus right, the left. Does that make sense for the product rule, or that method of using the product rule? Okay, good. And I did, hopefully you saw that the week 6 recording was uploaded, and I go over all 3 rules very carefully so that you know how to use it. Okay, let's finish simplifying by differentiating everything out. So still we have the cosine x over here minus the sine y dy dx. And then when we simplify the right side of the equation, so we're going to have x squared. What is d dx of y squared when we do this implicitly? Right. So the normal derivative rule would just be 2y. And then we remember the chain rule, because is y a function of x? Yes, Christina, you got it. After performing the derivative rule, we remember to multiply by the derivative of y. And then the second one's a little bit easier, right? Because we just have y squared, but now we're taking the derivative with respect to x to actually just something with it, only x's in it. So what's d dx of x squared? Exactly, so we just have 2x. So we can simplify the right side a little bit, where we have 2x squared y dy dx on that one, and 2xy squared. So who knows what we do now to finish solving the problem? Because originally we were searching for dy dx. And what we're going to do is we're going to treat dy dx as if it was just some sort of a variable. And then we solve for the variable using algebraic techniques. So what I'm going to do is I'm going to combine all the dy dx terms together. So we have this 2x squared y and this minus sign. I'm going to add the sign to both sides so I can get that. And then I'm going to take this, and I don't want it on this side. So then I'm going to move it on this side. And that's going to get all the dy dx's on just one side. So we'll have the cosine of x minus 2xy squared. And then we'll have 2x squared y dy dx plus sine y dy dx. Does that make sense? Just algebra here. And then what we do, we can now factor this out. So I'm going to kind of flip the equation around, but we have 2x squared y plus sine y dy dx. And this is equal to cosine minus 2xy squared. And then what's the final step here to isolate, to solve for dy dx? Exactly. We just divide both sides by whatever was in there. So we have cosine x minus 2xy squared all over the 2x squared y plus sine y. And that's it. So implicit differentiation is just an application of the chain rule. It's nothing too crazy. So what I think I'm going to do is I'm going to give you guys a problem. And I guess either does someone want to volunteer to solve a problem, or I can choose somebody. Okay, let's see. James, do you want to solve this problem? Okay, you can go ahead, come on, Mike.
Hello, can you hear me?
Mm-hmm.
First you do the derivative of both sides. And for the left side, you do the product rule.
Okay, and then what would that product rule look like?
X times the derivative of y plus y to the plus y times the derivative of x.
Excellent.
And for 1 over y, we can make it into y to the power of -1. So we can do that and then use the chain rule for for y.
And then how would we then differentiate d dx on the y when we rewrite with a negative exponent?
Negative y to the power of -2 times the derivative of y.
Excellent. Okay, what's the next step here?
Find the write the first one as it is, and find the derivative of x, which is 1.
So the derivative of this guy is going to be 1. What's the derivative of y here?
You keep it as like a variable kind of.
So we have just dy dx. So whenever you have something like this is always just going to be the derivative of dy dx. And then over here, you notice that the derivative of x is just going to be 1. And then I'm just going to put this like this. So then how do we now solve for dy dx?
Put the terms with dy dx on the same side, and the other one on the other side.
Like this?
Yes.
Okay. So
And
then
divide both sides by x plus 1 over y squared.
excellent. So dy dx, we have the minus y over x plus 1 over y squared. And obviously, if you wanted to mess around with the algebra, you could get something that looks a little bit different. Like we could multiply through by the y squared on top and bottom just to get rid of that. So we can have y cubed over xy squared plus 1. But yes, this is correct. If you had this as your final answer, that is correct. All right, thank you so much, James. Do you guys want to do one more problem of this, or does it make sense? Okay. Excellent. Well, what we'll do is we're going to take some time to talk about the first derivative test, because this is actually going to be, especially in AP calculus, first derivative test will 100% guarantee be on at least one, if not two, of the free response questions on the exam, and also at least several of the multiple choice questions. So first derivative test is a super, super big deal in calculus. It's one of the biggest and most useful and powerful tools that we can get from calculus 1. So the first derivative test. And really, what's great about it is that it's not super difficult. as all you really do is the name, and as the name insinuates, first derivative test, you take one derivative, okay? And the hardest part is being able to step back and understand how to then interpret what you're seeing, okay? So what we're first gonna do is we're gonna talk about calculus words in terms of if you read a word in a problem, that it has a very specific mathematical meaning. So for example, I don't know if you ever did this in like middle school or high school, but if they said, if you see the word of, this means multiplication, right? So like if someone said, 5% of 10 or 2/5 of 5, right? You would know that, okay, well then I just need to multiply those two values together. So the word of is not just an English word at that point. In the context of the math problem, the word of actually has, it correlates with an exact mathematical interpretation. You can translate that into the language of math. So we have something very similar in calculus. So we have words, important words that mean stuff. So these are going to be our calculus words. These are super important to understand. So if we say, so let's first let f be a function. If we're going to say that the function f is increasing, okay. Actually, I'm gonna write this in a different color because this is a really, really important word. Increasing. Increasing is a calculus word. And it's going to directly imply, so that the way we translate this, just how like if we read of, that means multiply. And actually this goes both ways. Is that if a function is increasing, this automatically gives us free information about the derivative, the first derivative. This means that the first derivative is positive. I'll do it. Is positive here. So increasing means the first derivative is positive. And this actually goes both ways, is that if we instead started with the first derivative is positive, that automatically means that f, the function, is increasing. And of course, if we have something for increasing, we have something for decreasing. So does anyone have any guesses? If we say that f is decreasing, what does that say about the first derivative, do you think? Exactly. That means the first derivative is going to be negative. And again, this goes both ways, right? Because if I instead just told you that the first derivative is negative, then you know the function is decreasing. So let's take a look at why we assign these words to the way that they are. So here's I'm going to sketch a function here. And I've color coded this function. So this is y equals f of x. And what we see is that in this function, the function is increasing here. And the reason we know that is because we can look at the graph. So that's the intuitive side of things. If you look at a graph of a function, you quite literally look for when it's literally just going up. If its value is going up, that the value is increasing, the function's increasing. Okay, so over here, it makes sense. We can look at the graph and we can say, well, the function is increasing, but then something happens here, something changes. Right? What happens at that point? Exactly. The derivative is 0, meaning that we have a horizontal tangent here. Now, on top of there being a horizontal tangent, this horizontal tangent is occurring at a very specific location. And I want you to see that's why I decided to color code it. There's no coincidence that the function changes from increasing to decreasing exactly at that point where the horizontal tangent is 0. And you guys see that? And so this is kind of the crux of how we interpret extrema and how we actually kind of define where we have local maximums and local minimums. So what we would call, so in this case, let's actually give this a name. Let's just call this A. What kind of extrema does the function have at x equals A? Is this a maximum or is this a minimum? Right, it's a maximum. So we would say that f has a maximum at x equals A. Okay, now what we're going to do is we're going to look at another possibility for how this can pan out. So suppose we had a function. If I can draw a straight line this morning. Okay. Now suppose we have a function that's decreasing. And then it changes to increasing. So again, let's observe the point, the point in time or the point along the x-axis where the function changes from decreasing to increasing. It changes right here. Now again, what's the derivative? What do we notice about this point? Let's call this b. Right? Well, what's 0? Right? The function itself isn't 0, but I know what you're trying to get at. Is that the slope is 0? The derivative is 0. Horizontal tangent. So in both cases, notice that we had over here, f, or I wrote that too close. F prime of A is 0. And same thing over here. We have that F prime of B is equal to 0. Now, what kind of extrema would we call this, right? Is this a maximum or is this a minimum? It's a minimum. So over here, we have that F has a minimum. At x equals b. So does everything make sense so far? Because this is where we're kind of building up to the reasoning, the reasons for why the test works in the way that it does. So if you have any questions about how we're interpreting this or what increasing means, what decreasing means, let me know. Or if we're all good, just also let me know. Okay, well, I'm going to assume that that it's okay right now. Actually, we can kind of reference these. So what we're going to do is we notice that we have the function changing from increasing to decreasing. So let's just note that. So f changes from increasing to decreasing. At x equals a. And then tell me what is going on in a similar vein with the second graph. F changes from what to what? Exactly. From decreasing to increasing. At x equals a. Now b. Now remember what I was talking about with these calculus words. What does increasing mean again about the first derivative? And what does decreasing mean for the first derivative? Exactly. And so what we're really saying when we write this, one way to think about that is, well, the derivative of the graph, it changed sign, right? Because if it's say over here with the maximum, if you have a positive first derivative and it's changing from positive, now it's negative, it had to change sign. In other words, and that makes sense, because if the derivative changes sign, it has to cross through the x-axis, meaning that the derivative has to hit 0, just as we found in both cases. You see? So does that make sense, right? going from that concept to that, moving to the next concept. Because when you change sign, you have to cross the graph at some point, right? Unless you just built in a jump discontinuity for no reason, right? But if you have a continuous function, a differentiable function, you're gonna have a crossover. And so what we do, and this motivates the entire test, this motivates the entire first derivative test, is that we search for these things called critical points. And when we find those critical points, and the critical point is basically looking very similar to like, when does the derivative equal 0? Because we can see clearly like here and here that extrema is only going to occur when the derivative is 0. And actually there is a caveat when sometimes the derivative is undefined, that you can have it. So for example, you could have a maximum occur at a little corner like this. The derivative isn't defined here at that peak, yet it is still a maximum. So we do look at the undefined place. So that is going to motivate the first derivative test. So we have the first derivative test. First derivative test. The first thing we're always going to do is we're always going to search for the critical points. Search for critical points. And we're going to define critical points here in just a second. Now, not every critical point will be an extrema, right? So these are just candidates. So it's kind of like bringing in a bunch of different candidates to apply for a job. You're not going to hire every single one all the time, but you got to narrow down the search. And then we're going to do and analyze how the function, or analyze the sign of the first derivative. At each critical point. And when we do that, that's going to give us the information necessary to say, okay, does this satisfy the criteria for being a maximum or a minimum, or maybe it doesn't. And then the last thing we do is interpret. Interpret analysis. So let's first define a critical point. Critical point. So a function f of x has a critical point at x equals, and then we just choose some point. So x equals c. If there are two things that could be true. If the first derivative of the function at c is 0, or if the first derivative at that critical point is undefined. And that's important because when we do the first derivative test, the most common mistake students will make is that they will forget to check the undefined if it's undefined. I mean, in most cases, you don't have to worry about that, but there are a good amount of functions where you can have an undefined first derivative And those locations need to be critical points and they need to be considered. And the absolute value function is a really, really good example of why we care about this side of the critical points. And actually, I might use that as the first example that we do. So actually, yeah, let's do that. So example. Oops. Find any extrema of f of x is equal to the absolute value of x. Who knows what the absolute value of x? I hope that's something that is relatively, familiar. It's just an idea. It's the v. So we can kind of sketch our bearings. We know that what the absolute value function looks like. This is x, this is y, and then this is y is equal to the function is equal to the absolute value of x. So what is the first step of the first derivative test? Well, the first thing we want to do is we want to search for critical points. So we're searching for locations where the slope is either 0 or the slope is undefined. So can you all find the critical point here for absolute value of x? Yes, x equals 0 is a critical point. Why is it a critical point, Christina? Well, the slope isn't 0 here. Exactly. It's an undefined slope because we're approaching on the left side here. We have this slope of like this constant -1. But then if we were to approach the slope from the right direction, we have a constant slope of +1. And then they meet in a corner. And so it never actually approaches the same exact slope on both sides. And so we have an undefined slope for that singular point because it doesn't approach any singular slope. Yeah. So does that make sense? Okay, awesome. Yeah. And so this is a critical point by definition because we just found a location where our function, the slope is undefined. So now what we do is we have our critical point is x equals 0. And now what we're going to do is we're going to go and look. So the second step is we're going to analyze the sign of the derivative at each critical point. So we only have one here. So I like to make these little line graphs to organize my information. So we have the slope, and we have then just x. So we know that right at x is equal to 0, right? So right when x is equal to 0, the slope is undefined. So I'm just going to say undefined. But that's okay. We just need to look now at what happens directly to the left and directly to the right. Because as you saw up here, the extrema was really about what? The extrema was really about saying, do we change the sign of the first derivative? Do we go from increasing to decreasing, or do we do the other? Do we do decreasing to increasing? But the point is, we're always searching for when the sign of the derivative is changing. Because if the sign of the derivative never actually changes as you cross past your critical point, you never got an extrema, right? You just got kind of this glancing slope in the thing. So over here, what is the slope of the function f to the left of x equals 0? So to the left of our critical point, what's the slope? Is it going to be, is the function increasing or is the function decreasing to the left of x equals 0? It's decreasing. And so decreasing, that's a calculus word. And what does that imply? Decreasing means what in terms of the derivative? Exactly, the derivative is negative. F prime is negative. So the sign of the derivative is negative on for all of this side of it. Now let's do the same exact thing. Check the right side. What about the right side? Right, the function is now increasing to the right of x equals 0. And so what does that mean for the first derivative? Increasing means derivative is positive, yes. Okay, and so here's where we ask ourselves, and when we do the interpretation, what's going on here? Well, what we say is that f is this going to be a maximum or is this going to be a minimum? Exactly. F has a minimum at x equals 0 because, so we now have to justify this. We can't just say it has a minimum and not prove it, right? The reason why we can say this is because f changes from what to what? Right. It changes from decreasing to increasing. At that point. And this is how we use the first derivative test. Decreasing to increasing will always mean minimum, and increasing to decreasing is always going to mean maximum. And here's the last thing we'll do in class is I'll show you a way to remember this and to keep it straight. So a maximum occurs when we go from increasing to decreasing. And one fun way I like to remember this is I draw, like if I think increasing to decreasing, we go from increasing to decreasing. And when I draw this little sketch on the side of the margin of my paper, I see, well, it's very obvious that this point here is going to be the maximum, right? Because we have to go up to it. It's like a peak, and then we go back down from it. This is kind of what I see going on in my head if I get twisted up. And then the minimum, what do you think the minimum is going to be? Yes. A minimum occurs when the function changes from decreasing to increasing. And that we can see because the function, we see it goes from decreasing to increasing. Now, obviously, these little diagrams here, they aren't supposed to be representative of how every single function is going to be. That's just more of a memory trick. So these over here, if you get confused, right? So if you ever do your analysis and you say, okay, I know that my function is going from increasing to decreasing. I don't want to, you're like, wait, is that the maximum or is that the minimum? Well, you can always kind of jog your memory by drawing like these little carrots, these little peaks and carrots on your paper just to make sure. But there'll come a point when the concept will solidify itself and you won't have to do that. But it can be a little fun thing just to see that it all works, that the math works, it all works together. So are there any questions about this first derivative test? And if it's about increasing to decreasing, or any questions about the critical points? Okay, awesome. I will leave you with one final note, is that in the example we did, there was no really moment when the derivative was actually zero. And that can sometimes happen. But in most cases, what you'll do is you'll find the first derivative, you'll take the first derivative of the function, and you set the first derivative equal to zero, because any solutions you get for that are candidate for their critical points. So does that make sense? Okay, awesome. So just generally speaking, if you have a function that you know is differentiable, just take its derivative, set it equal to zero, find those zeros. That's kind of the first step almost always. You get in that rhythm, and then double check to see if the undefined step works. Okay. Are there any other math related questions? Okay. Well, in that case, again, I think what I've noticed is that when you guys go through the morning messages, it's super easy to go do all that work and then you just forget to hit the like button. So if you have done lessons, make sure if you all just go quickly for like 2 minutes back to the website after class and make sure that the lessons that you have completed and then maybe just forgot to like, go ahead and do that so I have a better idea of where you're at, because I can't read your mind across the internet to see how many of the lessons you've actually done. So aside from that, that is all. I will see you all next week. If you have any questions, you can email me, or like Christina did, you can post to the discussion board. I'll see it there too. All right, thanks. Bye everyone.